Okay, once more. In a completely elastic collision, kinetic energy after equals kinetic energy before. There's no change in kinetic energy. In an elastic collision, the velocities before and after are equal, and the kinetic energy is minimal. Okay, if we go back to the previous example where we have 2 kilograms at 5 meters per second, 3 kilograms at -4 meters per second. If we have an inelastic collision, we can determine everything that happens. Okay, so again, total momentum before, which we calculated earlier, is -2 kilogram meters per second. 10 here and -12 here gives you -2. Okay, so what's the momentum after? Well, in an inelastic collision, and after the collision, these two objects are joined. So after collision, you've got these two objects with a total mass of 5 kilograms, 2 kilograms, and 3 kilograms. And can you see? Total after is total before, so the velocity you just have one velocity after, both of them have the same velocity, so the total momentum after is mass times velocity after. Total mass times velocity after. So velocity after times 5 kilograms, -2 kilogram meters per second. Divide by the 5 kilograms, you're left with -0.4 meters per second. Okay, we could analyze the kinetic energy after, but it's obviously going to be very low. Let's go ahead and do it. Okay, we do the 1/2 mv squared. Square that, you get 0.16 times 1/2 is 0.08. Multiply that by 5, you get 0.4 joules, if I did that right. Compared to the kinetic energy before, I'm just going to write it out. This is going to be 25 joules. And this is going to be 24 joules. You don't have much kinetic energy after. Now I don't remember what the solutions were. I'm looking back at what little bit I have here. But if you analyze the kinetic energy after in the original problem, or first problem, the one-dimensional problem, you find that the total kinetic energy after is fairly comparable to the total kinetic energy before. I took a quick look at it after I worked it, and I thought that it was going to come out a little less than what it was before, but not that much less. Now, the one thing it can't do, and let me repeat this, is it can't be greater than it was before. At least not unless there's some source of potential energy that gets converted in that collision. So these are ideas that are reinforced in the problems, in the Webb-assigned problems. Now this can be worked out in symbols. You see the book working things out in symbols. Again, that's a good thing. I think it helps to think through the quantities, at least when you're first getting used to it, but I've already commented on that. Okay, let me check my notes and see if there's something else. Yeah, and if you... And one reason I went to the pendulum analogy is that your text has a nice little video, happy pendulum versus sad pendulum. And there's a very good demonstration, a 1-minute demonstration. If you're not watching those videos, you're missing something because they're usually pretty good. Now, where was I? Okay, I'm going to close out by just doing the calculus of the situation. Newton's second law tells that net force equals mass times acceleration. Acceleration's derivative velocity with respect to time. If you have a constant mass, then this is just the derivative with respect to time of mass times velocity. So net force is the derivative of momentum, so that the integral from some initial time to final time of F net with respect to time is the integral from the same initial time to the final time of dp dt, so that the integral of force with respect to time, and maybe I should do one more step in there. And this is one really basic principle that everybody should understand so well in taking a calculus course that they can never forget it, but everybody just learns to do some calculations and forgets all the principles. And you want to try to do a little better than that. You want to maybe review the idea of the average value of an integral. The average value of the integral is the average value of f net is this integral divided by the time interval, the delta t, which is your tf minus ti. So if you multiply f average times your tf minus ti, your delta t, you get the integral. Okay? So it's one way of looking at the integral. It's really important for physical intuition, among other things. Okay? Now, integrating dp dt just gives you p evaluated between tf and ti. So your average force times delta t equals p evaluated at tf. Function notation, p evaluated at tf, not p multiplied by tf. Minus p at ti. Remembering that p is the symbol we use for momentum, mv. So that your average force times your delta t on an interval is the change in momentum. In other words, I really want to use a delta there, but I'll stick with your book. Impulse equals change in momentum. Looking for room to do one more thing here. If your impulse J is, let's say, 30 kilogram meters per second on a mass of 6 kilograms, with initial velocity of 4 meters per second, looking for room to do this, then your change in momentum equals your mass times your change in velocity. So your change in velocity is 30 kilogram meters per second divided by 6 kilograms. Which is 5 meters per second. So your final velocity is 9 meters per second. Another thing you can do, and we're out of time, but another thing you can do is, if you know the impulse and the time interval, in other words, if you know the impulse by knowing the change in momentum and you know the time interval, you can find your average force. So, if you know the change in momentum and the time interval, find the average force. So you're going to see problems of that nature if you haven't already seen them. Okay, well, good luck. We'll close in a second. I'm going to turn the camera off.